trait as parameters. Oh. Now that you know how to define and implement traits, we can explore how to use traits to define functions that accept many different types. For example, in listing 10-13, we implemented the summary trait on the news article and tweet types. We can define a notify function that calls the summarize method on its item parameter, which is of some type that implements the summary trait. To do this, we can use the implement trait syntax like this. So we can do a function, a public function notify item I see. In the function signature, instead of passing the concrete type, we can pass in the trait. We can say that this item, whatever it is, implements the summary trait, and then we can call the methods within that trait, which is, in this case, summarize. That makes sense. So that means we can write functions that are specific for the traits that we have. That is good to know. That is very good to know. Instead of a concrete type for the item parameter, we can specify implement keyword and the trait name. This parameter accepts any type that implements the specified trait. In the body of notify, we can call any methods on item that come from the summary trait, such as summarize. We can call notify and pass in any instance of news article or tweet. So yeah, that's the beauty of this right here, right? So this is a function, and typically in functions we pass in a parameter that is bound to a specific type. Well, in this case, we want it bound to a trait, and a trait can be applied to many different types. We have summary trait, which is applied to both news articles and tweets. Meaning that notify, we can pass in a news article or a tweet, and this will run just perfectly fine. Code that calls the function with any other type, such as string or i32, won't compile because those types don't implement summary. So if we call this function with anything that does not implement the summary trait, this will break, not compile. I like. Moving onward. Trait bound syntax. Implementation trait syntax works for straightforward cases, but is actually syntactic sugar for a longer form. Hold on. The implement trait syntax works for straightforward cases, but it's actually syntax sugar for a longer form, which is called a trait bound. It looks like this. What? So we have public function notify. We have our T summary, and we have item T. So we're saying this is a generic type that has implemented summary trait, and that T is going to be used for this parameter item. I see. That would be annoying to write, and thus implement trait is the syntax sugar that expands to this. The longer form is equivalent to the example in the previous section, but is more verbose. We place trait bounds with the declaration of the generic type parameter after a colon and inside angle brackets. The implement trait syntax is convenient and makes for more concise code in simple cases. The trait bound syntax can express more complexity in other cases. For example, we can have two parameters that implement summary using the implement trait syntax. Looks like this. So we had two. If notify took in two parameters and both of them implement summary, we would do something like this. Public function notify item 1, implement summary, item 2, implement summary. That seems pretty straightforward. However, if you want to compare it to the longer form, it's shorter now. The longer form is now shorter because we can do notify, we have the generic T, trait, summary, and then we say item 1 and item 2 are just of type T. That makes sense. I see why they're telling us this. So if we want this function to allow item 1 and item 2 to have different types, using implement trait would be appropriate as long as both types implement summary. if we wanted to force both parameters to have the same type, that's only possible to express using the trait bound syntax. Ooh, it's even deeper than I thought it was. So the real difference between these two is that for this one, right, item 1 and item 2 can be the same type, but they can also be different types, given that both of those types implement summary. Whereas for this syntax down here, this is saying that item 1 and item 2 are the same type, and that type implements summary. So this can be implemented on 2 tweets, 2 news articles, but not a news article and a tweet, while this one will allow for this to be a tweet and this to be a news article, because they both implement summary. Understood. The generic type T specified as the type of item 1 and item 2 parameters constrains the function such that the concrete type of the value passed as an argument for item 1 and item 2 must be the same. So yeah, they're saying that this T right here forces item 1 and item 2 to have the same type. Moving onward. This is just a lot of reading. I'm going to expand this. Specifying multiple trait bounds with the plus syntax. We can also specify more than one trait bound. Say we want to notify to use display formatting on item as well as the summarize method. We specify in the notify definition that item must implement both display and summary. We can do this using the plus syntax. So what they're saying here is maybe we want item to adhere to multiple traits. And if we want that to happen, then in the function signature, we say implement summary, which is the first trait, plus display, which is the second trait. For those who don't recall, I believe display allows us to print things to screen. I'm kind of fuzzy on that, but I believe that's what it's used for. The plus syntax is also valid with trait bounds on generic types. Okay, so in the other longer form of syntax, the long form syntax, we can use T summary plus display and then make sure that T adheres to both the summary trait and the display trait. Noted. With the two trait bounds specified, the body of notify can call summarize and use this thing to format item. So yeah, what I was saying was right. Display allows us to use this in the format when we're printing things out the screen. Clearer trait bounds with where clauses. Using too many trait bounds has its downsides. Each generic has its own trait bounds, so functions with multiple generic type parameters can contain lots of trait bound information between the function name and its parameter list, making the function signature hard to read. For this reason, Rust has alternate syntax for specifying trait bounds inside a where clause after the function signature. So instead of writing function signature, this thing, display plus clone, u, clone plus debug, tu being the parameters, and you return I32, we can use a where clause like this. Oh, this is much clearer. So function that takes the generic of t and u, little t is type t, little u is a type u, returns an I32 where t is implements display and clone, and u implements clone plus debug, and then the code block starts there. That makes sense. Okay, that makes sense. This function signature is less cluttered. The function name, parameter, list, and return types are close together, similar to a function without a lot of trait bounds. That's the where syntax. Gotta keep note of that. Returning types that implement traits. We can also use a implement trait syntax in the return position to return a value of some type that implements a trait, as shown here. So return summarizable, which returns a item, instance of something that implements the summary trait. And here we did it with the tweet because tweet implements summary. That makes sense. By using implement summarize for the return type, we specify that the returns summarizable function returns some type that implements the summary trait without naming the concrete type. In this case, return summarizable returns a tweet, but the code calling this function doesn't know that. The ability to return a type that is only specified by the trait it implements is especially useful in the context of closures and iterators, which we'll cover in Chapter 13. Chapter 13 used to seem very far away. Not so much anymore. Closures and iterators create types that only the compiler knows or types that are very long to specify. The implement trait syntax lets you concisely specify that a function returns some type that implements the iterator trait without needing to write out a very long type. Okay. So what they're saying here is that iterators hide a lot of these ugly function names and type things. Okay. However, you can only use implement trait if you're returning a single type. For example, this code that returned a news article or a tweet with the return type specified as implement summary wouldn't work. Oh, I thought it would initially when I was thinking about it, but I guess that's unfortunate. So taking a step back, what they said here is that in Chapter 13, we're going to learn about closures and iterators, and they are seemingly hiding a lot of these ugly function names that we just learned about, where you can have function, generic, parameter type, variable names, where clauses. Like all of that can be very long, and that's hidden behind iterators. Okay, we're just going to have to accept that until we get to Chapter 13. However, what they're saying here, which is more important, at least arguably, is that even if we declare the return type to be something that implements a trait, when we write our function body, we cannot return multiple types. So here in this case, we're trying to say, in one scenario, we want to return a news article. In another scenario, we want to return a tweet. Rust is going to yell at us. It says you can't do that. You can only return one type. Okay. Returning either a news article or a tweet isn't allowed due to restrictions around how the implement trait syntax is implemented in the compiler. We'll cover how to write a function with this behavior in the using trait objects that allow for values of different types section of Chapter 17. Wow, that was oddly specific. Okay, Chapter 17. That does seem like a long way away. I might forget about this by the time I get there. Okay. Fixing the largest function with trait bounds. Now that you know how to specify the behavior you want to use using the generic type parameter bounds, let's return to listing 10-5 to fix the definition of the largest function that uses a generic type parameter. Last time we tried to run that code, we received this error. And it was missing partial order. I do remember that. Are they going to show us the code again? They do. They show us the code down there. Cool. In the body of largest, we wanted to compare two values of type t using the greater than operator. Because that operator is defined as a default method on the standard library trait standard compare partial order, we need to specify partial order in the trait bound for t so that largest function can work on slices of any type that can compare. We don't need to bring partial order into scope because it's in the prelude. Change the signature of largest to look like this. Alright. So what they're saying here is that in order to fix this code, the code from 10-5, which we can't really see right now because that's way back when, pretty much in that code, to refresh your memory, we were trying to compare two things. We were trying to see if one number is larger or greater than another number. But in order to do that comparison, we need a specific trait, and that trait is partial order. And in this section, we learn how to bind our generic types to a trait. We can use the where clause, or we can just use this syntax because it's only just one. So we can say that function largest has a generic t that's bound or implements the partial order trait, which is in our prelude, so we don't have to import it directly. It's already imported for us. And then we can continue with the function as is, seemingly. This time, when we compile the code, we get a different set of errors. Okay, we haven't compiled the code because we can't see the code, but that's fine. So this says cannot move out of slice t, a non-copy slice. Keyword copy. Key context, because context wasn't actually given to us again, is that when we first wrote this function, we were acting on integers, I32, and chars, which I believe are I8. Those by default have a copy trait, which we read way back when, that pretty much means that we don't have to clone them like we do with strings. They're not on the heap, they're on the stack. And anything on the stack, if it needs to be moved over or moved, like Rust moving, then we create copies of them. But that ability or that defined functionality is within the trait copy. So seemingly, we're just going to add a copy trait to it. So let's see what they say. The key line in this area is cannot move out of slice type t, a non-copy slice. With our non-generic versions of the largest function, we were only trying to find the largest I32 or char, as discussed in the stack-only data copy section in chapter 4. Yes, chapter 4. Types like I32 and char that have a known size can be stored on the stack, so they implement the copy trait. But when we made the largest function generic, it became possible for the list parameter to have types in it that don't implement the copy trait. Consequently, we wouldn't be able to move the value out of list 0, the index 0, and into the largest variable, resulting in this error. So yeah, because this is generic, there exists a scenario where the type that's being passed in does not have the copy trait, and because it does not have the copy trait, we're not allowed to move it. So in order to fix that, they seemingly just add a copy. To call this code with only those types that implement the copy trait, we can add copy to the trait bound of t. Enlisting 10-15 shows the complete code of a generic largest function that will compile as long as the types of the values in the slice we pass into the function implement the partial order and copy traits like I32 and char do. And here's the full code, so let's write that out. Let's scroll down. And I don't think we need any of this anymore. I guess the function main needs to come back, but let's start with largest, right? Largest. So for largest of generic type t, we are binding it to the trait's partial order, and then we're adding another trait called copy, which I guess is in the prelude because I didn't have to import it. We have our parameter, which is a list, and it's a pointer to a slice of type t, and we want to return an instance of type t, right? And then we continue with the rest of the function. Largest equal to list 0, we're copying it over, but we have the copy trait, so it's good. And then for, we're using references because we're dealing with references for item in list.iter. and it did that thing again that I don't like. For item in list.iter, if the item is greater than our current largest, then we need to redefine our current largest. Largest is equal to item, and then we're returning our largest. And we need our main function back. We have let number list equal effect 34, 50, 25, 100, 65. Cool. Let result equal largest, and we pass in a pointer to our number list. And we're going to print out I need a line. The largest number is result. Let char list vector using the macro, creating our chars, y. We follow the convention this time. No more YMCA. A Q. Let result equal largest, pointer to our vector. This is our char list. And print line, which is going to be this more or less the same. The largest char. Largest char is result. And let's run that to make sure it works. And we got an error. Cool. And I misspelled iter. And y is the largest char, and 100 is the largest int. So it is working code. That is confirmed. If we don't want to restrict the largest function to the types that implement the copy trait, we can specify that t has the trait bound clone instead of copy. Then we could clone each value in the slice when we want the largest function to have ownership. Using the clone function means we're potentially making more heap allocations in the cases of types that own heap data like strings, and heap allocations can be slow for working with large amounts of data. So what they're saying here is that another way to make it work, because we need ownership at this point in time, right here, and I guess here we need ownership too, is that we could use clone. And in the case of clone, we have the potential of making a lot of heap allocations, which could make our code slower. But technically speaking, because of the items that we're working on, I32 and chars, we don't need it. We don't need it. Another way we can implement largest is for the function to return a reference to a t value in the slice. If we change the return type to a pointer to t instead of t, thereby changing the body of the function to return a reference, we wouldn't need the clone or copy trait bounds, and we could avoid heap allocations. Try implementing these alternate solutions on your own. So after a 10-minute session of trying to implement one of these alternate solutions on my own, I think I've been set up. I'm not sure if it's possible to do this with information that we already know, at least if we try to do the case of removing clone and copy. But I could be wrong. I'm not sure. Moving onward. Using trait bounds to conditionally implement methods. Okay. Let me just make this bigger. Using trait bounds to conditionally implement methods. Using a trait bound with the implement block that uses generic type parameters, we can implement methods conditionally for types that implement the specified traits. For example, the type pair of some generic type t in listing 10.16 always implements the new function, but pair t only implements the compare display method if its inner type t implements the partial order trait that enables comparisons and the display trait that enables printing. This sounds complicated. I mean, in practice, it doesn't seem all that bad, but if I were to write something out, this could get hairy quick. So what they're saying here is, so let's just walk through this real quick, right? They implemented display, or they didn't implement display. They imported display, this trait. They have their struct pair, which is of a generic type t, right? They have their implementation block, which acts on the generic types that t can be. Anything that t is, it acts on it. And we have a new function to create new instances of pair. You pass in t and t, and then you get yourself a pair, right? But then we also have a second implementation block that has a new method called compare display, but that can only be called when t implements both display and partial order. So if the t type does not implement both display and partial order, you can't call this. You don't have access to this. It's kind of cool in the way it kind of encapsulates what you want in your functionality. You don't want to be able to call something like this when you can't use it. And you know the cases when you can use it. You can only use this when the type t implements both display and partial order. So this makes sense in terms of how generic it is. But at the same time, I'm not sure if I like it. I mean, I'm probably going to learn to love it. It's going to save me a lot of time and testing. But still, on a side note, an example of something that supports both of these can be integers, chars. I'm not sure if string does, but integers definitely, like I32, you can order them and you can print them to screen. We can also conditionally implement a trait for any type that implements another trait. So given that t implements the trait display, we can then create a implementation block for the toString trait for t. So anything in here is going to have both the display trait as a default, and this is giving the implementation for the toString trait. That's kind of cool, kind of confusing in terms of the way you say it, but it makes sense. It just means that any t that's in this implementation block is going to have access to or be able to use display, because all these t's satisfy the display trait. I'm not sure if I read the next sentence. So implementations of a trait on any type that satisfies a trait bounds are called blanket implementations and are extensively used in the Rust standard library. And then you give an example. For example, the standard library implementation of toString trait on any type that implements the display trait. And that looks something like this. The implementation block in the standard library looks similar to this following code. Okay. Because the standard library has this blanket implementation, we can call the toString method defined by the toString trait on any type that implements the display trait. For example, we can turn integers into corresponding string values like this because integers implement display. So what this syntax is actually, the meaning of the blanket part of this is that anything that implements the display trait has access to the toString methods. Cool. And as such, strings, or integers, I should say, they implement the display method unless you can call toString on them, which is a method within the toString trait. And I'm guessing I32 probably has their own implementation of it, but more or less, that makes sense. Blanket implementations appear in the documentation for the trait in the implementors section. Traits and trait bounds let us write code that uses generic type parameters to reduce duplication, but also specify to the compiler that we want the generic type to have particular behavior. The compiler can then use the trait bound information to check that all the concrete types used with our code provide the correct behavior. In dynamically typed languages, we would get an error at runtime if we called a method on a type that the type didn't implement. But Rust moves these errors to compile time, so we're forced to fix the problems before our code is even able to run. Additionally, we don't have to write code that checks for behavior at runtime because we've already checked at compile time. Doing so improves performance without having to give up the flexibility of generics. Okay, that makes sense. So what they're saying here is that because of this implementation of generics and blankets and traits in general, this is taking away a class of errors that in dynamically typed languages will be found at runtime. And if you find anything at runtime, it typically means that these errors found while the program is running, which could imply that these are errors found while your code is out there in production. What Rust is saying is that we've taken those errors, those possible errors, and moved them to compile time, so that your code won't even compile. You'll be forced to fix these errors well before you put your code in production. That is great. The last paragraph. Another kind of generic that we've already been using is called lifetimes. Rather than ensuring that a type has the behavior we want, lifetimes ensures that references are valid as long as we need them to be. Let's look at how lifetimes do that. And this was a long video and really wordy, really wordy. But I learned a lot. I hope you did too. Outside of that, have a good night. Peace. Wait, have a good night. I don't know if it's night there. Have a good rest of your day. Peace. Again.